Okay, good morning and welcome back. I hope you had a wonderful sleep last night. So now we have the opportunity to have the third keynote speaker for this year's Biometric Conference. And the keynote speaker is someone very special because he's not only well known in the academic community, but he's also have been serving a very good bridge for the academic community and the industry. And the speaker is of course, someone you know well. That is Jean-Christophe Fondeur from Morpho. As I said to Christopher yesterday, he is well known to all of us, but still I want to spend a few minutes to give you a very brief introduction about Jean-Christophe. So Jean-Christophe is the VP, as you know, for Research and Technology for the Identification Division of Morpho, a well-known company in the field of biometrics. He has been leading Morpho's biometric research activity for more than 12 years and actually has been involved in all of Morpho's major breakthroughs in biometrics in the past 18 years or longer. So his achievements are multifold, and that include in particular the development of biometric algorithms and of innovative biometric sensors, the implementation of biometric algorithms in smart cards, or the design of scalable architecture for very large biometric systems, such as the FBI and the UID project in India. He holds more than 13 patents in the field of biometrics, and is a member of several learned societies, including the ICB and the IPR. So today he will tell us how to make biometric research going succeed from the lab to large-scale deployment. So without further ado, I would pass the floor to Jean-Christophe, please.
So thank you very much, Professor, and thank you to all of you. I'd like to start with starting the organizer for this excellent event and for giving me the opportunity to talk to you this morning. I also want to thank all of you for being here at 9 o'clock in the morning after a flamenco evening and all the nightlife possibilities in Madrid. Very impressive. So thank you for that. I will try to keep you entertained for the next 45 minutes or next hour or so. So, as Tianyu said, I mean, I don't think we need to spend much time explaining the activities of Morpho, but in a nutshell, so we develop product and technologies and integrate them in very large systems in the field. So, I think we are in a very special position because we have in-house researchers, research teams, so PhDs and people doing algorithm and research, and at the same time, we are in touch with the most concrete deployment in the field and face all the operational problems. So what I want to do in this keynote is not so much explain in detail such or such technology that we are developing, but more to illustrate the attitude that we try to have, maybe explain or share some of the things we see in the field and how we try to solve them at the level of the technology. So trying to develop algorithms or sensors or technology that can help bridge the gap. I mean, yesterday Christophe Fondeur was talking about bridging the gap between biometrics and forensic community. In a way, I'd like to try to make a bridge between the field and operation and the academic or more fundamental research. So very, very simple way, mostly two parts. First part, maybe the fun, entertaining part will be sharing some of the large-scale deployment that we've made and trying to illustrate the situation that we face. And in the second part, trying to derive from there a couple of technical approach that try to answer some of those problems that we face in the field. So another way to say it, maybe in a little more detail, I mean, obviously we all know biometric, three main operations to perform: the enrollment, the deduplication, the verification. So that's That's the application view, what we talk with the customers and the people who deploy the system. So enrollment can be supervised, controlled, unsupervised, many variations. Same for the deduplication, several possibilities, and the verification. So that's kind of how we structure the discussion with a customer. On the other side, we have the technologies that we have at our disposal to develop those projects, and they are mostly around data capture, so acquisitions and sensors. They are a lot about algorithms, all type of algorithm, from compression, quality, coding, matching, and all that type, tracking, all that type of algorithmic operations. And then the decision level, because once we have made those operations, then we need to make an operational decision to be able to provide an answer to what the customer is interested in, which is it the same person, or... So there's a lot of work as well at the decision level. So another way to say it, so challenging situation, and we'll talk about field condition and scalability and tuning of the algorithms and variability in the data and that type of thing, and trying to look at those two sides and how they interact with one another between what happens in the field and what we can do at the technology level. So my hopes are, beyond entertaining you for 1 hour, maybe to share some experience, and mostly for the younger researchers, explain what the situation can be in the field. I guess those of you who have been in the business for a long time, you will not necessarily learn a lot. But I think it's important, especially for the younger generation of researchers, to have an experience and a feedback on what's going on in the field. And so that's one of the goals, to sort of share this experience. Another one would be to maybe more proactively challenge or raise your interest on such or such problems, so that you can help either solving them or taking them into account when you develop a new algorithms or a new technology, and say that somebody will need to take care of that at some point. Maybe not you, but it's always good to know that you know what needs to be done before the system or the technology can go outside. So a couple of examples of operational challenges. And first, as the title is from the lab to the field, I'd like to say just a few words on the lab. So the very cliche view of the lab is, the researchers in lab coats and very calibrated sensors, controlled environment, and things like that, but maybe less intuitively. There's a lot of lab-type assumption that we do on a day-to-day basis in the signal processing or in the things we do. I mean, on the data side, the distribution are often Gaussians, and the noises are white, and the variables are independent, and the users are cooperative, and they are not trying to behave in a funny way, or they are trying to help you, whether in most situations helping you is not their problem. They just want to do their own business. So all of those situations, to me, are behind this lab condition. Representativity of data set, of course, is something very typical. Very often we work on small set, 40, 100, 200 people, and that makes sense. But it also makes sense to try to measure or to realize the biases or the lacks that are between the reality and what happens in the world and those data. And that's one of the points I would like to emphasize. So enough said about the lab. Go to a couple of real life projects. The first one I'd like to mention is a project that I believe was one of the most challenging biometric system ever. Maybe only India recently took it at another scale and at a much bigger scale. But that's a project I was involved in 1995, 1997. That is not very known in the community, and that's in South Africa. And the goal of the project was to do biometric verification to deliver pension payment on a monthly basis to millions of citizens. So I can show you a small video. I will show you a small video there, but in a nutshell, the big number, so several millions of people to enroll in a few months, and then monthly verification. So for those of you who work on biometric, you know, or you probably don't, I don't know, but authentication has this particularity that when you deploy a system of authentication in the field, people will complain when there is a false reject. When you enroll people, if you have bad quality or if you fail finding duplicates, people will not complain. So you don't have a real-time feedback from the operation when your algorithm misses something. When you do a false reject on a system on which the people rely on to get their monthly money, then any false reject becomes very dramatic and can create very, very stressful situation for everybody. So that puts a lot of pressure on the accuracy side. So that's a video of typically what we do. So we have sort of ATM system on trucks that go from villages to villages. So you can imagine a lot of heat and dust and sometimes humidity, sometimes very cold temperature. You have those, so this is 1995, so that doesn't look very modern, but that was almost 20 years ago. And so one of the first projects of that type. So people queuing all day long and getting their fingerprint taken with very involved operator, because any false reject is a problem, so the operator is trying sometime on a way that would be unacceptable for many of us today, but at the time that's the type of situation that you had to do when you wanted to have a false reject rate operational in the field in a few less than 1%, I would say, maybe 0.5% or something like that, on pension payments, so mostly elderly people in extreme conditions. So, as I said, the characteristic and being in a project like that, so I will come back a little bit on the history. I started, as Jean mentioned, in 1994, developing algorithms and also being involved on developing sensors. So out of school, working on theoretical algorithms and an eye sensor. And then a few years after, we have this opportunity, first deployment of authentication system, first deployment of like optical fingerprint sensor in the field, and I'm asked to be the project manager for this, so it was excellent opportunity and very educative opportunity for me. And you see a lot and you learn a lot in situations like that. For example, you learn that people, whoops, I'm going the wrong direction. Oops, sorry about that. I will manage at some point. Yeah, you learn that sometimes the temperature is above 50 degrees and that the operators, to make the sensor able to work, they wrap it in a humid piece of stuff so that it cools it down so that they can operate it. You learn that you see sensors coming back from the field that are completely burnt out and used by the people putting their finger again and again and again. You see many situations like that. You realize the stress of the operator because of the security issue. Of course, there is a lot of money on these trucks, so there are armed guards everywhere, sometimes helicopters to protect the situation, and every now and then you would have attacks and casualties, so you realize that the operators and people operating that cannot concentrate only on trying to get the best fingerprint image quality. They have to be careful for their own life. And so you realize that if you ask too much to the operator in certain situations, that will not work. And so the algorithms and the sensor must take some of this burden on their side. So a lot of situations like that. Of course, dealing with a lot of not IT-aware population, multiple languages, So anything that you need to explain or feedback or explaining how to interact with the sensor, again, a lot of challenges. So a lot of that has been seen more recently in many projects, including the UID project, that is, to me, a little bit like this project, but like 100 times bigger. But this was 20 years ago and very, 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 very educative, so I wanted to share that, that type of experience with you. Another example, so that's a mass enrollment system for voters enrollment. So what we're trying to do is to enroll the population and make sure they don't ask for multiple voting cards. So that's a typical system that where biometric can be very useful to the government of countries, and I would say to the propagation of democracy overall as a very social oriented tool. So again, you're in the field, you have no electricity, you need to deploy everything in a tent, and you have a lot of again, dust, sun, and things like that. So very challenging. The more recent one, so I will not go to the end of that one. A more recent one, as of end of last year in Kenya, same type of project. So again, always the same beautiful, exotic images, but beyond those very picturesque images, there's a lot of operational challenges hidden. So this one, 14 million enrollment in 1 month. So same type of project, but compressed with a very compressed time frame. So that means also field condition, but so that means that you need to train 30,000 operators to operate the system. So again, if you think that you can train them, that the core and the deltas must be visible and that the image must be ICAO compliant and all that type of thing, that's not going to happen. You cannot train in a few weeks 30,000 people to do something very sophisticated in terms of biometric. So again, you need to take that burden on your side when designing the system. Last but not least, of course, you've had a presentation on that on the UID system. So as I said, it's like the combination of all the previous one, 10 times 100 or 1,000. So very, very exciting and very impressive project in which I had the chance to be very involved in the very beginning, talking with the program team to help them realize what's difficult, what's not difficult, what's feasible, what's not difficult, the different options. And so typically we had discussion on should we use 1 finger or 10 fingers or fingerprint and iris, should we use face, should we use rolled fingerprint or 1,000 PPI sensors, all that type of discussion and very nice interaction with the program team, I must say, on building together on a period of less than a year, coming from the idea of enrolling the complete idea to almost the first prototype. So I know many people in the room, or several people in the room were involved in this project as well. One of the characteristics that was not mentioned so far on this project, I mean, several one, the scale, I'm going to get back to that in a few minutes, but you see typically on the right-hand side, very young people to enroll, so all the biometric looks very different on kids than on adults. Not very different, but scaling problems and things like that. So again, that means your algorithms must take into account different frequencies in the data, different type of problems, scaling, invariance, and things like that. On the scale, I was mentioning the scale. What you see on the left is the forecast, and actually the system deployment is going a little bit faster than that. That was planned at the beginning of the project. So typically, we were targeting 200 million enrollment per year. And so when you accumulate, so that's the blue curve, and when you accumulate that over time, you have a quickly growing database going to 1.2 billion at the end. So those are the numbers. Numbers are numbers. When you try to compare what it is compared to the current state of deployed systems somewhere, that's what we're trying to represent there. On the top right corner, you see the database size. In green, you see the largest biometric database size to date, excluding the UID. So you have typically like the FBI database or the US visit database are in the 150 million people. Those are the largest biometric database to date. And the goal of the project was to go in 2012, 200 millions. So the unit is crores, it's an Indian unit, number of units. It's 1 crore is 10 million people, so 20 is 200 million people, and reaching at the end over 1 billion person. So you see the gap between even the first step of what we want to do in the system and the largest systems that are deployed in the world. In addition to the gap in the database size, there is also a gap in throughput in terms of what you're trying to do with the system. The largest throughput that are handled in biometric system on a regular basis, I'm not talking peak value, but on a regular basis, again for those big systems I mentioned, are in the 100,000 searches a day, typically 100, 200,000 searches a day. What we're trying to do here is 1 million searches a day. So as you know, because you're all scientists, basically the computational power that you need is basically the product of the database size and the throughput you're trying to reach. So as you have a several-fold increase in database size and in throughput compared to the largest system ever, what we are trying to build here is a system that is 10 to 50 to 100 times bigger than the bigger system ever deployed. So that again raises a lot of questions on, is it feasible just from a physical point of view? Can we build a system that can run fast enough so that we don't need 100,000 blades to operate it? But also biometric questions on how will the performance hold when we go on such large systems. And again, you see my point of this link between the operational question and problems that we face in the field and what we can help solving or explaining. And so that's kind of what I will try to illustrate in my second part. And basically trying to emphasize, so typically on this type of situation, as I explained, if you wrap the sensor into a wet piece of stuff to cool it down, so that's typically operation level. So a lot of problem can be addressed at the operation level by the people, local people deploying the system. Most of them are very involved and they want to make things work and they will be very imaginative to solve a lot of problems. That's one issue, but we cannot only rely on that. If we go one step before, we can try to address some of those problems at the integration level. Integration level is a customer has a need, we take the bits and pieces of technologies and equipments and software that exist and we put that together to solve what the customer asks us to solve. So when doing that, again, we can try to anticipate the problems we can face and we can try to build that system in a way that some of those problems will be solved. But again, not all the problem can be solved like that. And I think this is where this community can play a role, is some of those problems can only be addressed at the design level before. If the information is lost or if the problem is not fixed at the design level, you can do whatever you want. At the integration or operation level, you will not be able to be very successful. And so that's what I will be trying to illustrate on a couple of examples. So first part, you had examples of situation, and now I will take sort of a transverse view with examples of problems to be solved and how they can be solved at those three levels. So first example that we faced, extreme sunlight. You've seen that we are often deploying systems in outdoor, very harsh environment, so the sunlight can be very, very strong. And for most of the biometric sensors, or all of the biometric sensors, if you do nothing, you will have serious problem. Because the light will create shadows, saturation, reflection. It will blind your sensor, and that's true for just a normal camera to capture face. It's true for an iris sensor, and it's also true for a fingerprint sensor. So they will work up to a certain point, and then when the light becomes too strong, you would see artifacts. So what can you do about that? Well, at the operational level, of course, you can try to build a tent or a shelter and try to protect from direct sunlight. Of course, you can do that, and of course, you have to try to do that in as many situations as you can. At the integration level, you can try to put a cover on your sensor so that it's built-in protected against the direct sunlight. So typically when you build your device, you try to work on the shape and the ergonomy so that you can protect from there, and then you don't need to try to find an external shelter. But what can we do at the design level to avoid those situations, or in addition to those situations, I would say? So one example, and again, my point is not to pretend this is the best solution. It's just to illustrate one way you can try to address a problem at the design level. So typically that first idea you could have would be to try to outpower the sun. Well, good luck with that. You can try, but to some extent the sun will always win at the end. So alone it's not sufficient, but you can try to be clever in designing your system. One thing you can do is, most of the system, if you do an active lighting, you can choose the wavelength that you're using, and you know this wavelength, so you can put a passband filter so that you filter out all the sun energy that's outside what you know you have sent. And so you know what you get is coming mostly from what you have sent, and then you can gain an order of magnitude of power against the sun. This is classical, typical, but this is often not sufficient. Something else you can do is to play with the time. A camera, you can try to illuminate and integrate the image on a continuous basis, but you can also try to flash all the energy at a very short period of time, and if you open the camera shutter just in a synchronous way with this flash, then you save again against the sun, because the sun is illuminating on a continuous basis, so the ratio between the shutter opening and the rest, again, you gain another order of magnitude. And you can go even one step further. You can try to do funny things, like you keep the flash idea, but one image you would flash and one image you would not flash, or you would flash outside the shutter. So you would have, you see on the right-hand side, when you illuminate, you see a fingerprint image with your illumination. On the previous one, you have no illumination, so what you see comes from the outside. So as long as you operate, and if you've done all the previous one, you come back to a more linear, non-saturated way, then you can subtract the two and further increase the robustness to this lighting. So that's one illustration of how you try to solve at the design level a problem that you face in the field. And that's the kind of thinking and idea that if you're not aware, I can tell you that the first sensor that we built for this South African project, we didn't think of that. We deployed in the field, and we had this problem, and we had to go back in the lab and rethink everything and re-engineer over a few months to think of solution like that, to be able to deploy something that will be able to work outside. So again, that's one of the reasons why I like to share that with you, so that you can try to think a little bit like that and anticipate that type of problem. Another example with the environment, it's about fingerprint capture and humidity. If you have a very wet finger, or those of you who have played with fingerprint sensor, when you try to capture fingerprint, you would have a very nice uniform black blob, which is not what you expect to see. So again, you need to deal with that. So the first way to deal with that is you tell your operator, you know what, if you see that, you ask the person to dry their hand, and you're done. Again, when you're in the field, you maybe don't have stuff with you, or if you have to make sure that you are physically secured and make sure maybe you don't want to explain 100,000 people a day that they need to dry their hand. You can try to work that at the integration level. Typically, you would try to detect that, do quality measurement, and try to build in the system some measures that will send some warning to the operator and say, hey, something goes wrong, the finger is wet, so please do something. That's one step before, and that's certainly something we need to do. But again, we need to try to do something at the design level. So the example I've chosen is with total internal reflection sensors. So I don't know if you're familiar with that type of technology, but basically you illuminate through a prism a finger, you put your finger on the platen, and if you observe beyond a certain angle, typically the angle that depends on the index, optical index of your finger and of the platen, you can only see theoretically light coming from the inside. So either diffused light or reflected light from inside. So typically that's how most of the optical sensors work. Well, the problem is if you don't pay too much attention, if you have water and the water index is between the index of the finger and of the glass, then the water will behave like the finger and you will see this black blob. So you can study, and that's what you see on this side, this angle compared to the index, and you can study that for the finger and for the glass and for the water. And if you choose appropriately the index and the angle, then you can make sure that the water behaves like the glass in a way and not like the finger. And so you will sort of remove all or some of the water effect from that. But again, if you don't anticipate, and again, when you first develop a sensor, you don't anticipate that type of thing, then you have the problem. And again, that's where experience and sharing that type of feedback is useful so that people can take that into account in their design. Another example, so those examples are on the sensor side, the first one, maybe not primarily your field, but this is concrete and physical, so it helps understanding the message. Next topic I'd like to address is robustness or dependence on the type of data. Typically, what you see there is what you expect to see in a typical system. So forensic system, you expect to see nice fingerprints and nice faces. What you see in real life is sometimes a bit different. You may have text on your finger, or this is swipe sensor, so you may have funny artifacts in the image, or you may see an infant image which is much smaller, or you can see a non-frontal image or a cropped image, or sometimes you can see a latent, or sometimes you see that type of image. Tip of fingerprint is missing, and this is sent to your system just as if it's a fingerprint. So all those type of, or you can get images like that, and all those type of situations happen all the time, of course, and you need to deal with them one way or the other. So at the operation level, of course, if you want to be sure to have a frontal image, well, you can move the camera in front and make sure that you have a frontal image. Or you can, as you've seen in the movie in the South African project, you can take the fingerprint of the person and put it on the platen, and then you know that it will be flat and well positioned and that you will see the center and you will have no problem. But that's not always very convenient and not always possible. So you can, to try to mitigate a little bit that, you can try to do things like certifying the sensors or certifying the application, so that's at the integration level, so that all the application make the same control the same way, and all the sensors have been certified so that they behave the same ways and the images look the same and that type of thing. Or you can try to predict if what you see is what you expect to see. You will see later today a paper from from Michigan State on fingerprintness, trying to have quality measure to say, hey, is what I'm seeing a fingerprint? Because that's what you expect to see. And if it's not, then you can try to do something, raise an alarm. And then that helps us integrate in the system to deal with that. But what can you do at the design level? That's one question. And on that one, I must say, it's more an open question that I raise than an idea that I bring, because more and more we rely on learning techniques in the field of biometrics. And learning techniques are very nice, and you can separate the variables and the classes and do stuff very nice, but it depends a lot on the training set. And if on your training set you only see those images and what you are presented in the field is somewhere there, what will be the reaction of your classifier? You don't know, but it can be very bad, because the classifier can tell you, I'm pretty sure this is the same person, because it falls in the right region of the classifier. And typically that type of problem we see very often on many algorithms, and I'm not expecting a machine learning based algorithm to be able to recognize everything, but I would like this algorithm to be able to recognize that what it sees has never been seen before. I'm pretty convinced this is feasible, and that should be done more often, but this is something that we must do, and that's a very weak point today of machine learning techniques in the real world, is that if you don't try to put barriers to make sure that that type of situation does not occur, you can have your algorithm leading you to a completely wrong situation. So how to solve that, I don't know, but I'm sure there are some nice theoretical and practical problem beyond that. Couple of more problems are variability that we have to deal with, scale. So again, I'd like to share a couple of thoughts or ideas and challenges about scaling. So we've seen in the Indian project when nobody has seen a 1 billion person fingerprint or iris database. So nobody can predict or can know for sure, or can measure, I should say. Nobody can measure what the performance will be, of course. So we need to rely on trying to extrapolate and that type of technique. And again, the scientific community can and must help on that type of analysis, because that's very critical for a system to be able to anticipate the level of performance that will be reached, and if we go one step further, to know whether a system will just work or not. And when you invest on a system that need to be scaled at the scale of India or complete country, you'd rather know before that it's going to work, because if you only know after that it doesn't work, that's not a very nice situation. So again, all the IT problems and scaling and data center and administration I will not detail here, but they are quite significant in such systems. I will more focus on the biometric accuracy and how you can try to extrapolate and predict what's going on, and a few ideas around that. So first, a preliminary comment about the metrics. I will be 2 or 3 slides on that topic, so I wanted to introduce the metrics. So you know all of them, but there are, to me, mostly, if you look at the biometric system as a black box, 3 main characteristics from a systemic point of view. You have, of course, the accuracy, false match rates, false match rate that you see at the end. You have the throughput, the speed of your system, which is critical in the design, and you can do quality control and reject some of the data if you see that it's not a fingerprint or quality is too poor or something like that, and that's the rejection rate. And of course, they are all linked together. You can easily trade false match against non-false match, false non-match by adjusting the threshold. You can trade speed versus false non-match by changing the parameters of the algorithm, making it faster but less accurate, or slower but more accurate. And you can reject more. That will increase your operational accuracy, but you have the drawback of rejecting people. And so my point here is all of that is nothing to do with, or not much to do with the technology. It's just different tuning and policies on one set of technology. But often there is a confusion between tuning and improving the technology. So I just want to exclude the tuning. I would say it's necessary, it will be done, but what I'm interested in is what we can do to improve, not to change the parameters, the trade-offs. So again, at the operation level, when you scale, that's very easy in a way. If you have more comparison to do and you have more verification to make at the end, you can line up the servers and you can line up the operators, and then you have your solution. Maybe not the most economical, viable solution, but that's something you can do up to some point, and that's something that you do, but you want to keep that as the last way to do that. At the integration level, you can play with all those trade-offs and try to trade false match against false non-match and accuracy versus speed and rejection so that you design a system that is the best trade-off that you can do. But what can you do at the design level again? I think on the scientific side of it, we need to do at least two things. One is, as I said earlier, trying to predict and to be able to extrapolate. So there are multiple ways of doing that, some statistic models or some more empirical ways. Typically, you take small database, and then a bigger one, bigger one, bigger one, and then you measure the accuracy, and there is some theoretical background behind that. You say in a log, it's more or less a linear scaling, and then you can use that to sort of predict your accuracy, and not only predict, but also analyze. Typically, you see that so this is an example with 2-finger performance on a specific database, 4-finger and 6-finger. And what you see when you do something like that is that not only when you have more biometric information, you have better accuracy that you would expect, but you also scale better because the slope basically is flatter, so that means the more accuracy you have, the better you scale. And this is one, actually, of the slide we used with the Indian customer to explain that instead of going for 1-finger or 2-finger, going for 10-finger and iris, that's good because you add information, so you will scale better. So you improve, but you scale. I think one of my, so typical, yeah. From there, of course, you can predict on a larger data set what the accuracy would be. And I think one thing that could be interesting to you as well when you develop an algorithm or a technology, even if you work on a small data set of 40, 50, 100, 200 people, I think it's useful to try to extrapolate because the conclusions on the value of a specific algorithm may not be the same if you look there or if you look there. And I think there is certainly a value of trying to extrapolate to make sure that maybe a couple of percent there are not very important, but if your algorithm can change the slope and make it a lot flatter, then something that will be just marginal on a small data set, if when extrapolated that becomes big, that has a lot more value in terms of power of the technology. And again, so I don't know how to do that, but typically this type of flatness of the dead curve or the rock curve is a good indication. So the coefficient basically of this regression is a good indication of the robustness to scaling. So this was an example with different type of information or quantity of information. This is on an internal data set. This is an example from a NIST test on latent matching. And you see here a couple of biometric algorithms. So it's not a dead, it's a rock curve. So it's like reverse. So the best algorithm should be flat and high. And so you see, again, the way different algorithms vary. So it's interesting not only to compare, as I said earlier, an algorithm at a given point of operation, but to try to see how it behaves when you go much lower in the false accept, which sort of simulate a larger data set, or when you try to extrapolate. And you see that two algorithms that may look close at this operating point, they are quite significantly different when you go on the lower false accept, so when you go to larger data sets. And I think it's interesting to realize that even if your data set is not huge and maybe not completely representative, it's interesting to realize that extrapolating may change the conclusions on the best tuning or the best value for an algorithm. And so maybe trying to extrapolate more, to optimize more in this part of the graph unless you have a large data set, than in this part of the graph. Last point I wanted to make, again on the matrix and scalability, is to try to go beyond the dead curve and the ROC curve. So 20 years ago, at the time of this South African project I mentioned at the beginning, everybody was talking equal error rate, and every system had an equal error rate of 0.0000001%. Okay, that was the beginning of the technology. Lack of maturity on how to measure, and lack of maturity on what to look at. And typically, to try to summarize the complete performance of an algorithm in one point, that was obviously not enough, especially when that point, like the equal error rate, is not really linked to an operational scenario. So at that time, the ROC curves and dead curves were introduced, and that's a better way to compare the algorithm, because you can really see the technology improves. But when you want to go to an operational system, that's not sufficient, because you're not implementing a dead curve. You need to choose a threshold when you set a system. And most of the time, you need to choose it a priori, not after, when you've seen the distribution of the results, and then you can choose your threshold. See what I mean? So what you can do with that at the operation or integration level, of course, you can tune online, because of course your system is repeating sort of the same operation days after days after days. So you can start with something, and then every day try to readjust and make sure that your system is still tuned correctly. But another better way would be to have a stable and a normalization on all the factors that can vary in a system. Again, that's an extract to illustrate that. So NIST is doing a lot of research along those lines. So that's from the IREX-3 report from NIST. And you see here the curves for different conditions of recognition. This is on a database, one eye on a small database, 160K eye. Then you go to 1.6 million and 4 million, so database size increases. And this is for 2 eyes. And so what happens when you don't do correctly the normalization, or you don't try to correct for that? You see the 4 million performance is there, and if your database is only 1.6, you have almost a ratio of 5 on the false positive of your system. And the false positive, you may not be aware of that, but I should have mentioned that. That's very important in an operational system. That's in an identification system, that's basically the level of security of your system, because that's the number of people you will let go through your system, or that's the level of manpower you will need to make to do the verification. So that's a critical indicator. And when it goes like that, when the database changes, database size changes, if you do, like in the Indian project, 20 million new enrollment every day, that means every day, every hour, you will have to adjust your threshold and compensate for that. And if somebody has 2 eyes and sometimes 1 eye, then again, your score distribution will vary a lot, and operationally, you are taking decisions on some things that are very different. If you try to normalize that and take into account that factor, of course, you can stabilize all that, and then whatever the conditions are on the database size and on the number of eyes, then you can try to stabilize that. So I've wanted to make that last point, because very often in the community we talk dead curves and ROC curves, and we think we're done. We're mostly done, but there is a little more to do, and it would be nice to try to model that. So I was discussing that with Sebastian yesterday, introduced the, extra EPC curves, so EP curve, extrapolated performance curve, or expected performance curve. That may be a solution to that, trying to measure the effects a posteriori of a threshold that you choose a priori, and see how well you can predict. I didn't have time to read in detail, but maybe that's an option. But that's the kind of feedback that I would expect from these communities, to be able to bring some measures, either some measures that can capture that type of problem, or measure that type of problem, or algorithms that are robust to such variation. And of course, this is just the database size or the number of finger or eyes, but there are a lot of parameters that can vary and that we need to take into account and normalize everything so that everything is as predictable and stable as possible. So that concludes my talk. I think I've been through all I wanted to share with you this morning, sharing the challenging situation, emphasizing the different way to implement solutions. Some are at the operation level, so that's typically the job of our local partners or operators. Some are at the integrator level, but some are at the design level, and that's where we need your input, because robustness is critical. Maybe my message, concluding message would be, in some situation, 5% or 3% improvement maybe is not as important as increased robustness. Maybe I'd prefer to lose 1 or 2% of accuracy, but have all those problems solved, than to have something that has minimal variation of accuracy in a very specific condition, but that cannot be generalized at all in other conditions. So that's it. Thank you.
Thank you very much, Jean-Christophe, for sharing with us your very valuable first-hand experience with so many practical problems in biometric applications. That's cool. Thank you very much.
Pretty good.
I already noticed you have your hands up, please.
You mentioned in your African project that operators felt threatened, I guess, because they carried a lot of money. But from those people who enrolled, did anybody try to spook the system, or everybody was, cooperating? Did you have any those type of occurrences?
You find all type of situation. You realize that sometime, together with the enrollment of one guy, you will find the operator's finger reversed so that you cannot find it when you match it. But the guy can still get money from the system by putting his finger like that. You see a lot of funny situation on that.
And so algorithmically you try to solve all those cases, or how did you handle them?
Same, some at the operation level, so you can put some supervision on some specific things that you see on the system, or some level of activities. At the integration, you can try to check, and more now with the data mining techniques, trying to detect funny things happening and try to analyze that in real time, and as well along the time to localize maybe areas or people where more problems occur. And again, at the system level, trying to build in and your algorithm so that they are typically trying to detect all that type of things and as early as possible. But good question.
Thank you. You were in an interesting topic for me concerning the scalability of verification systems. Can you say a couple of words maybe on the training issue as well, when the scale is varying extremely? I'm thinking about that if you have designed a system which is heavily relying on machine learning algorithms, how easy it is to incrementally update to newer situations. Can you tell us a little bit about your experience on how complex a machine learning algorithm is allowed to be under those circumstances? So when the training needs to be done maybe recursively.
So I'm not sure if I understand your question from scalability or from upgradability point of view, but from upgradability point of view, for sure, if you have to relearn regularly, then you have to re-encode the database or deal with the legacy that has been processed already, and that can be indeed a problem. In some of the situations, typically fingerprint or iris, you can try to modify when you upgrade mostly the matching side and not try to change the data side, which is a heavier operation. I don't know. So that's for the upgradability of the systems. In terms of scalability, I don't see really the link with the with the machine learning algorithm, beyond the fact that when you scale, you see more unexpected data, and so you need to make sure when training your system that it generalizes well and that you have not overtuned on a specific situation. And of course, the bigger the data set, the more you will see that problem.
In your lab, we know we can guarantee the quality of biometric symbols, and they are make sure the recognition is pretty good. And in the practical system, besides the quality of biometric symbols, what is the challenging issue? Or if we access the biometric quality and discard the low quality biometric symbols, the recognition method have been good enough?
I think in a project like India, I mean, you have all the possible problems that you mentioned. I mean, you have the.
You mentioned most of method about the fingerprint. I think. What about other biometric trees, or face and iris and some other?
I'm not sure I understand your question.
I think he was asking, you spoke a lot about fingerprints.
Yes.
Yes, the problem with the fingerprint and challenges of solutions. What about other modalities?
Well, I speak a lot of fingerprint because that was my background, and so most of the examples that I've known at the technical level are on the fingerprint side, but we have the exact same problems that in all the biometrics, in iris, on the scalability. I mean, John Dogman has worked a lot, again, on the stability of the distribution and the shape of the tail, and the illumination problem I've mentioned. They are the same in iris and fingerprint and face in most of the biometrics. So most of the problems and all the one I've mentioned, especially at the end, the stability of the threshold was iris, and so they all are shared with most biometrics. Yeah.
Okay, thank you.
And so in India, we have the 3 biometrics or 2 biometrics running in parallel. So in one of the systems, you have face and iris in parallel, and in the other one, we will have soon face, iris, and fingerprint in parallel. First one is fingerprint and iris in parallel. So again, the fact that we run everything in parallel, then you have the 2 biometric compensating for each other's problems, either on the quality or weaknesses of the algorithms or scalability or that type of thing.
Thank you.
Yes.
Thanks for your talk. For your South Africa project, I'm just wondering if you had some people without fingerprint. In this case, what happened?
So so obviously, like in all biometric problem, you need to have a way to handle exceptions, as we say, and you want to have as little exception as possible. So in this project, I remember, because the number were quite impressive, the number of people we could not enroll was 1 in 1,000. We wanted to have at least 2 fingers out of 10, and we would try. You've seen how hard we try on the operation, taking the finger and doing that. At the enrollment side, we would use all the pads and things and try. So you had normal, typically what you do, you have normal enrollment station, where you do the normal processing, where you try to have most people going through quite quickly, and when you have difficulties, then you go like in secondary inspection or secondary enrollment area, where you try to do something more specific. Today we would probably try to use different sensors or different things, but at least you can try to put more pressure and spend more time to try to get the data. So we had 1 in 1,000, and as I said, in verification, one in a couple of hundred tries would fail, and then in this case you would go for a manual process. But same in India. I mean, most people, they have either fingerprint or iris, but I mean there are exceptions, and there are opportunity or occasions where you have no fingerprint and no iris that you can use, and then you have some specific, and then the people need to go on a specific place to collect their money or to get enrolled, and so that's the type of thing you need to do when you deploy a system. You will always have exception, and so you need to have one way or one process to handle them.
Your example are rather, as you said, are rather fingerprint-based applications. Do you have some other field applications of that scale? For example, using face.
Well, so face we have a lot because on every single ID system that we do, like the one you've seen, you capture face as well. You don't always use it for verification, but so all the problems you find at the enrollment side, whenever you have an ID document, you print the face. So for 20 years, we've been capturing face in all type of situation. Not so much for matching at the time, and now as face images are available everywhere, you can plug a backend system matching and comparing the faces in many of the systems. But I didn't so much illustrate that because it's not as visual as what you can see in operation like that when you are in the desert and in the field and you can really feel the extreme conditions. But
thank you very much. I think it's about time to stop here.
I'll stop.
I do see one more hand in the ears. Perhaps you can talk to Jean-Christophe during the coffee break.
Yeah.
During the coffee. So thank you very much. So let us join hands to thank the speaker once again. Thanks very much.
Thank you.
So we have a half an hour coffee break and then we have the oral session. So please come back.